operating system, is described as a symphony conductor, because OS coordinates the sharing and use of all the components in the computer. Learning outcome. At the end of this topic, students should be able to explain operating system functions and components, identify characteristics of modern operating system. Understanding OS component. Processor manager, CPU, I/O or device manager, keyboard, mouse etc. User command interface. File manager, secondary storage. Network manager, communication, protocol etc. Memory manager, main memory, RAM. Understanding OS component. At the base of the pyramid are the 5 essential managers of every operating system: the processor manager, the memory manager, the file manager, the I/O or device manager and the network manager. Each manager works closely with the other managers and performs its unique role regardless of which specific operating system is being discussed. At the top of the pyramid is the user command interface, from which users issue commands to the operating system. Regardless of size or configuration of the system, each of subsystem managers shown in Figure 1.0 must perform the following tasks: monitor its resources continuously, enforce the policies that determine who gets what, when, and how much, allocate the resource when it's appropriate, reallocate the resource when appropriate. OS components, user command interface. The program that reads and interprets control statements is called variously. CLI, command line interface, is an interface that accepts type command. User has to write a command, a line at a time. Some common commands in Unix are cd, cp, ls. In MS-DOS ADA, copy, md. GUI, graphical user interface, is an interface that allows the user to activate operating system commands by clicking on desktop icons or menus using a pointing device such as a mouse or touchpad and screen. Use in Macintosh and Windows. Its function is to get and execute the next command statement. OS components, processor manager. The processor manager decides how to allocate the central processing unit, CPU. An important function of the processor manager is to keep track of the status of each process. A process defines as a program in execution. The processor manager monitors whether the CPU is executing a process or waiting for a read or write command to finish execution. Once the processor manager allocates the processor, it sets up the necessary registers and tables and, when the job is finished or the maximum amount of time has expired, it reclaims the processor. The processor manager has 2 levels of responsibility. One is to handle jobs as they enter the system and the other is to manage each process within those jobs. The first part is handled by the job scheduler, the high-level portion of the process manager, which accepts or rejects the incoming jobs. The second part is handled by the process scheduler, the low-level portion of the process manager, which is responsible for deciding which process gets the CPU and for how long. OS components, memory manager. It is a repository of quickly accessible data shared by the CPU and I/O devices. Main memory is a volatile storage device. It loses its contents in the case of system failure. The OS is responsible for the following activities in connections with memory management. Keep track of which parts of memory are currently being used and by whom. Decide which processes to load when memory space becomes available. Allocate and deallocate memory space as needed. OS Components, Networking Manager. Access to a shared resource allows computation speed-up, increased data availability, enhanced reliability. Communication takes place using a protocol. The processes in the system are connected through a communication network. These resources include hardware, such as CPUs, memory areas, printers, tape drives, modems, and disk drives, and software, such as compilers, application programs, and data files. Network Manager provide a convenient way for users to share resources while controlling users' access to them. OS Components, I/O Device Manager. The Device Manager monitors every device, channel and control unit. Its job is to choose the most efficient way to allocate all of the system's devices, printers, ports, disk drives and so forth based on a scheduling policy chosen by the system designers. I/O Device Module keeps track of the status of devices, I/O traffic controller. Each I/O device has a device handler that resides in a separate process associated with that device. OS Components, File Manager. The File Manager keeps track of every file in the system, including data files, program files, compilers and application programs. By using predetermined access policies, it enforces restrictions on who has access to which files. Also controls what others are allowed to do with files once they access them. For example, a user might have read-only access, read and write access, or the authority to create and delete files. Managing access control is a key part of file management. Finally, the File Manager allocates the necessary resources and later deallocates them. OS Components, Cooperation Issues. Each manager not only performs its individual tasks, it must also be able to work harmoniously with every other manager. For example, let's say someone types a command to execute a program. The following major step must occur in sequence. Step 1. The device manager must receive the electrical impulses from the keyboard, decode the keystrokes to form the command, and send the command to the user command interface, where the processor manager validates the command. Step 2. The processor manager then sends an acknowledgement message to be displayed on the video monitor so the user realizes the command has been sent. Step 3. When the processor manager receives the command, it determines whether the program must be retrieved from storage or is already in memory, and then notifies the appropriate manager. Step 4. If the program is in storage, the file manager must calculate its exact location on the disk and pass this information to the device manager, which retrieves the program and sends it to the memory manager. Step 5. The memory manager then finds space for it and records its exact location in memory. Once the program in memory, the memory manager must track its location in memory, even it is moved, as well as it's executed by the processor manager. Step 6. When the program has finished executing, it must send a finished message to the processor manager so that the processor can be assigned to the next program waiting in line. Step 7. Finally, the processor manager must forward the finished message to the device manager, so that it can send a message to the user. No single manager could perform its task without the active cooperation of every other part. They must cooperate to succeed. Microkernel architecture. A microkernels developed in the 1980s when the first usable local area networks being introduced. The main function is to provide communication facility between the client program and the various services that are also running in user spaces. New services are added to user space and do not require modification of kernel. Provide more security and reliability. Commonly used in embedded applications. OS services would be implemented as user space programs to allow them to be worked on monolithically and started and stopped like any other program. Microkernel architecture. Microkernel allows the addition of new services. Microkernel design imposes a uniform interface on requests made by a process. It is flexible because features can be subtracted to produce a smaller and more efficient architecture. Modular design helps to enhance reliability. The microkernel supports distributed operating system and object-oriented operating system. Multithreading. Threads is known as lightweight process and used in implementing network servers. Multi-threaded applications programs contain several threads running at one time that have same or different priorities. Examples: web browsers and time-sharing systems. A thread is contained inside a process. Thread of execution is the smallest unit of processing that can be scheduled by an operating system. Multiple threads can exist within the same process and share resources such as memory. On a single processor, multithreading generally occurs by time division multiplexing, as in multitasking. The processor switches between different threads. On a multiprocessor or multi-core system, the threads or tasks will actually run at the same time, with each processor or core running a particular thread or task. Symmetric multiprocessing, SMP. Symmetric multiprocessing, SMP, is a computer architecture that provides fast performance by making multiple CPUs available to complete individual processes simultaneously. Multiprocessing. Unlike asymmetrical processing, any idle processor can be assigned any task, and additional CPUs can be added to improve performance and handle increased loads. With proper operating system support, SMP systems can easily move tasks between processors to balance the workload efficient. A variety of specialized operating systems and hardware arrangements are available to support SMP. Specific applications can benefit from SMP if the code allows multi-threading. SMP uses a single operating system and shares common memory and disk input-output resources. Both Unix and Windows NT support SMP. Each CPU in an SMP system can act independently. While one CPU handles a database lookup, others can update the database and perform other tasks that can increase the ability of the device. The microkernel supports distributed operating system and object-oriented operating system. Object-oriented programming language-based. Object-oriented design. Kernel resides in memory at all times, performs essential tasks, and protected by hardware. Kernel reorganization. Memory resident, only for few essential functions, such as process scheduling and memory allocation. Modules, all other functions, such as device allocation, are not allowed to reside in main memory at all time. Advantages: modification and customization without disrupting integrity of the remainder of the system so that software development can be more productive. Object-oriented programming language-based. Early OS. Entire operating system in main memory. Available memory for applications. Early operating systems, A, loaded in their entirety into main memory. Modern object-oriented systems, B, load only the critical elements into main memory and call other objects as needed. Object-oriented OS. Operating system kernel in main memory. Memory allocation module in main memory, if needed. Available memory for applications. File management module, available. Device management module, available. Networking module, available. Conclusions. Operating system has 5 essential components and each of it have its own responsibility. Operating system component and functions has work interoperability between its component. Modern operating systems characteristics has aligned with the hardware technology.